The Moon is Earth's only natural satellite. At about 1/4 the diameter of Earth, comparable to the width of Australia, it is the largest natural satellite in the solar system relative to the size of its planet, the fifth largest satellite in the solar system overall, and is larger than any known dwarf planet. The Moon is a planetary mass object that formed a differentiated rocky body, making it a satellite planet under geophysical definitions of the term. It lacks any significant atmosphere, hydrosphere, or magnetic field. Its surface gravity is about 1/6 of Earth's, 0.1654 grams. Jupiter's moon Io is the only satellite in the solar system known to have a higher surface gravity and density. Orbiting Earth at an average distance of 384,400 kilometers, 238,900 miles, or about 30 times Earth's diameter, its gravitational influence slightly lengthens Earth's day and is the main driver of Earth's tides. The Moon's orbit around Earth has a sidereal period of 27.3 days. During each synodic period of 29.5 days, the amount of visible surface illuminated by the Sun varies from none up to 100%, resulting in lunar phases that form the basis for the months of a lunar calendar. The Moon is tidally locked to Earth, which means that the length of a full rotation of the Moon on its own axis causes its same side, the near side, to always face Earth, and the somewhat longer lunar day is the same as the synodic period. That said, 59% of the total lunar surface can be seen from Earth through shifts in perspective due to libration. The most widely accepted origin explanation posits that the Moon formed about 4.51 billion years ago, not long after Earth, out of the debris from a giant impact between the planet and a hypothesized Mars-sized body called Theia. It then receded to a wider orbit because of tidal interaction with the Earth. The near side of the Moon is marked by dark volcanic maria, seas, which fill the spaces between bright ancient crustal highlands and prominent impact craters. Most of the large impact basins and mare surfaces were in place by the end of the Imbrian period, some 3 billion years ago. The lunar surface is relatively non-reflective, with a reflectance just slightly brighter than that of worn asphalt. However, because it has a large angular diameter, the full Moon is the brightest celestial object in the night sky. The Moon's apparent size is nearly the same as that of the Sun, allowing it to cover the Sun almost completely during a total solar eclipse. Both the Moon's prominence in the earthly sky and its regular cycle of phases have provided cultural references and influences for human societies throughout history. Such influences can be found in language, calendar systems, art, and mythology. The first artificial object to reach the Moon was the Soviet Union's Luna 2 uncrewed spacecraft in 1959. This was followed by the first successful soft landing by Luna 9 in 1966. The only human lunar missions to date have been those of the United States Apollo program, which landed 12 men on the surface between 1969 and 1972. These and later uncrewed missions returned lunar rocks that have been used to develop a detailed geological understanding of the Moon's origins, internal structure, and subsequent history. The usual English proper name for Earth's natural satellite is simply the Moon, with a capital M. The noun moon is derived from Old English mona, which, like all its Germanic cognates, stems from Proto-Germanic 22 mensis month, from earlier meneses, which may be related to the verb measure, of time. Occasionally, the name Luna, lune, is used in scientific writing and especially in science fiction to distinguish the Earth's moon from others, while in poetry Luna has been used to denote personification of the moon. Cynthia, Sn Theta I, is another poetic name, though rare, for the moon personified as a goddess, while Selene, Slini, literally moon, is the Greek goddess of the moon. The usual English adjective pertaining to the moon is lunar, derived from the Latin word for the moon, luna. The adjective Selenian, slinin, derived from the Greek word for the moon, selene, and used to describe the moon as a world rather than as an object in the sky, is rare, while its cognate selenic was originally a rare synonym but now nearly always refers to the chemical element selenium. The Greek word for the moon does however provide us with the prefix seleno, as in selenography, the study of the physical features of the moon, as well as the element name selenium. The Greek goddess of the wilderness and the hunt, Artemis, equated with the Roman Diana, one of whose symbols was the moon and who was often regarded as the goddess of the moon, was also called Cynthia, from her legendary birthplace on Mount Cynthus. These names, Luna, Cynthia and Selene, are reflected in technical terms for lunar orbits such as apollune, pericynthian and selenocentric. Isotope dating of lunar samples suggests the moon formed around 50 million years after the origin of the solar system. Historically, several formation mechanisms have been proposed, but none satisfactorily explained the features of the Earth-Moon system. A fission of the Moon from Earth's crust through centrifugal force would require too great an initial rotation rate of Earth. Gravitational capture of a pre-formed Moon depends on an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing Moon. A co-formation of Earth and the Moon together in the primordial accretion disk does not explain the depletion of metals in the Moon. None of these hypotheses can account for the high angular momentum of the Earth-Moon system. File. Evolution of the Moon.org. The evolution of the Moon and a tour of the Moon. The prevailing theory is that the Earth-Moon system formed after a giant impact of a Mars-sized body, named Theia, with the proto-Earth. The impact blasted material into orbit about the Earth, and then the material accreted and formed the Moon just beyond the Earth's Roche limit of approximately 2.56 R. This theory best explains the evidence. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations also show that most of the Moon derived from the impactor, rather than the proto-Earth. However, more recent simulations suggest a larger fraction of the Moon derived from the proto-Earth. Other bodies of the inner solar system such as Mars and Vesta have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth. However, Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated. The impact released energy and then the released material reaccreted into the Earth-Moon system. This would have melted the outer shell of Earth, and thus formed a magma ocean. Similarly, the newly formed Moon would also have been affected and had its own lunar magma ocean. Its depth is estimated from about 500 kilometers, 300 miles, to 1,737 kilometers, 1,079 miles. While the giant impact theory explains many lines of evidence, some questions are still unresolved, most of which involve the Moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotopic signatures of lunar rocks. The rocks from the Apollo program had the same isotopic signature as rocks from Earth, differing from almost all other bodies in the solar system. This observation was unexpected, because most of the material that formed the Moon was thought to come from Theia, and it was announced in 2007 that there was less than a 1% chance that Theia and Earth had identical isotopic signatures. Other Apollo lunar samples had in 2012 the same titanium isotopes composition as Earth, which conflicts with what is expected if the Moon formed far from Earth or is derived from Theia. These discrepancies may be explained by variations of the giant impact theory. For instance, a high-speed drive-by hit by the impactor allowed it to return to Earth a second time but more slowly, and mix more thoroughly. A hit-and-run and return scenario might be more likely. The Moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth, due to gravitational anomalies from impact basins. Its shape is more elongated than current tidal forces can account for. This fossil bulge indicates that the Moon solidified when it orbited at half its current distance to the Earth, and that it is now too cold for its shape to adjust to its orbit. The Moon is a differentiated body that was initially in hydrostatic equilibrium but has since departed from this condition. It has a geochemically distinct crust, mantle, and core. The Moon has a solid iron-rich inner core with a radius possibly as small as 240 kilometers, 150 miles, and a fluid outer core primarily made of liquid iron with a radius of roughly 300 kilometers, 190 miles. Around the core is a partially molten boundary layer with a radius of about 500 kilometers, 310 miles. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests a crust of mostly anorthosite. The Moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about 50 kilometers, 31 miles thick. The Moon is the second densest satellite in the solar system, after Io. However, the inner core of the Moon is small, with a radius of about 350 kilometers, 220 miles, or less, around 20% of the radius of the Moon. Its composition is not well understood, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the Moon's time variable rotation suggest that it is at least partly molten. The pressure at the lunar core is estimated to be 5 gigapascals, 49,000 atmospheres. The topography of the Moon has been measured with laser altimetry and stereo image analysis. Its most extensive topographic feature is the giant far-side South Pole Aitken Basin, some 2,240 kilometers, 1,390 miles, in diameter, the largest crater on the Moon and the second largest confirmed impact crater in the solar system. At 13 kilometers, 8.1 miles deep, its floor is the lowest point on the surface of the Moon. The highest elevations of the Moon's surface are located directly to the northeast, which might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins such as Imbrium, Serenitatis, Crisium, Smythe, and Oriental possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about 1.9 kilometers, 1.2 miles, higher than that of the near side. The discovery of fault-scarp cliffs suggests that the Moon has shrunk by about 90 meters, 300 feet, within the past billion years. Similar shrinkage features exist on Mercury. Mare Frigoris, a basin near the North Pole long assumed to be geologically dead, has cracked and shifted. Since the Moon doesn't have tectonic plates, its tectonic activity is slow and cracks develop as it loses heat. The surface of the Moon is an extreme environment with temperatures that range from 140 degrees Celsius down to minus 171 degrees Celsius, an atmospheric pressure of 10 powers to 10 pascals, and high levels of ionizing radiation from the Sun and cosmic rays. The exposed surfaces of spacecraft are considered unlikely to harbor bacterial spores after just one lunar orbit. The surface gravity of the Moon is approximately 1.625 meters per square second, about 16.6% that on Earth's surface or 0.166 grams. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly persist in cold, permanently shadowed craters at either pole on the Moon. Computer simulations suggest that up to 14,000 square kilometers, 5,400 square miles, of the surface may be in permanent shadow. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the Bastatic radar experiment located on the Clementine spacecraft indicated the existence of small, frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. Volcanic lava beads, brought back to Earth aboard Apollo 15, showed small amounts of water in their interior. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice, using the onboard Moon Mineralogy Mapper. The spectrometer observed absorption lines common to hydroxyl, in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1,000 ppm. Using the mapper's reflectance spectra, indirect lighting of areas in shadow confirmed water ice within 20 degrees latitude of both poles in 2018. In 2009, LCROSS sent a 2,300 kilogram, 5,100 pounds, impactor into a permanently shadowed polar crater, and detected at least 100 kilogram, 220 pounds, of water in a plume of ejected material. Another examination of the LCROSS data showed the amount of detected water to be closer to 155 plus or minus 12 kilograms, 342 plus or minus 26 pounds. In May 2011, 615-1410 ppm water in melt inclusions in lunar sample 74,220 was reported, the famous high titanium orange glass soil of volcanic origin collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this announcement affords little comfort to would-be lunar colonists. The sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ion microprobe instrument. Analysis of the findings of the Moon Mineralogy Mapper, M3, revealed in August 2018 for the first time definitive evidence for water ice on the lunar surface. The data revealed the distinct reflective signatures of water ice, as opposed to dust and other reflective substances. The ice deposits were found on the north and south poles, although it is more abundant in the south, where water is trapped in permanently shadowed craters and crevices, allowing it to persist as ice on the surface since they are shielded from the sun. In October 2020, astronomers reported detecting molecular water on the sunlit surface of the Moon by several independent spacecraft, including the Stratospheric Observatory for Infrared Astronomy, SOFIA.